Alright, so okay, this should be small. UKT, this is fine. Need to fix all the typos. So this is a small k, and this is also, yeah. So GitHub, there's the main file. Inside the training loop, what we do first of all is we create a batch tensor, target tensor. We just mem copy. We can slice, use the slice columns and concatenate columns function, which is just written over here, but we'll look into that later. So first of all, we calculate this tensor scores, tensor image, and then clip gradients. So yeah, these are the lines that I need to add over here. Right after this batched, yeah, we have these lines. So right after the batch tensor, we just copy, we just calculate attention scores, and then we just attention score, and this is attention score. Tensor check, clip gradients, and then tensor check. So clip gradients and then tensor check. Perfect, perfect. This is good. Attention is score. Batch tensor is fine. Attention is score. Attention is score. Print. And exit. Attention score. What is this? Dear. Wow. Strange. Wow, it's strange. Sometimes it works and sometimes it doesn't. So this has to do with the, I guess, the seating issue, maybe. Or there's some ghost error associated with this memory allocation. Let's see how exactly are we allocating the memory over here. So this is our main file. So inside, okay, so inside this loop, batch tensor is working just fine. Batch versus embedding dimensions, this is just working fine. And batch tensor and mbatch, what shape does this mbatch has, and what is this mbatch first of all? Okay, so what is this M batch? First of all, this M batch is embedding dimension, batch size, number of heads. Um, this was exactly something we were doing over here. We created this tensor create new. We had created this batch number of head sequence, then the embedding dimension. Over here it was working just fine. Over here it was working just fine. And what exactly is wrong with this forward, with this training loop? Now the issue is with training loop, not with the MHA forward. Main C, and let's just see. Tensor create new batch and target batch tensor. Shape is fine. Attention is score. Batch tensor. Uh, Wait a minute. Wait a second. What shape do we have for batch tensor? Let's just see. It's not printing shape. Are you serious? Batch tensor. Batch tensor. Batch tensor. Is it something? Oh, sorry, we're not printing a shape. Instead, we're just getting it 2D and getting it. What shape do you have? 1632. Attention scores. Let's just see what's wrong over here. Um, is there anything wrong with our arena allocation of tensors array? So in case if I go to the tensor.c file and see this tensor concat, concat. So where exactly is this method where we are actually appending each tensor's output to some array which I created using, so basically it's a dynamic array created using arena alloc, and the dynamic array is of tensor pointers, right? So I think there's something wrong with this array allocation, or is it? Let's just figure out. Okay, so we have um, arena and okay, so what's wrong here? Okay, so where have I actually uh, done that? So yeah, there it is. So let's just create using malloc, maybe mha number of heads times size of tensor, and just uh, okay, so hmm, yeah, uh, heads array is like this, and then we store head score like this. So first thing is this, and the other thing is inside arena we need to create a method called void arena reset, and it's gonna take arena pointer, and what it's gonna do is it's gonna that's it. Now the question is, will this work? If you reset Arena, and I have this really terrible habit of closing the file each time and closing the next, opening the other file. I can do this just using command mode, and with E command I can just navigate between the files easily. But yeah, let's try to build this habit. Okay, so first of all, what I'm gonna do is just, let's do it. Arena reset A, arena reset, arena.h, and arena, let's say reset, and all it takes is arena. Seg fault, batch tensor, segmentation fault. Should we test it individually first? Okay, so this is our batch tensor, which is supposed to work fine because nothing is too special with this thing. Here's something special, and we're exiting. That's correct. That is correct. So we're receiving a seg fault issue over here. Okay. MHA forward, and yeah, let's just run this now and see if it works as per our expectation. Again, something is wrong. Randomize, initialize parameters, multi-head attention. And what this does is basically malloc number of heads times size of tensor pointer. That's correct. That's correct. Let's just verify if this method is correct. And you know what? I think I should bring all this here, or I can also delete that. Let's just delete this. We don't need this anymore. So yeah, this looks fine. This looks fine. Now let's just verify whether this method works fine. Mm, tensor slice and tensor concatenate. This is working fine. Or is it? Let's check it. Let's confirm that each time after slicing and after concatenation we are getting the tensor's correct shape and also the data. So inside tensor what we have is we have this thing, So let's just check this. So tensor randomized heads k and dk, and so what is this? This is actually a new line and out chunk and yeah, out chunk, right? And next is we don't want to concatenate. Okay, so need to print the initial uh, tensor as well. So the actual tensor is tensor get 2dx and print. This is our actual tensor, and yeah, uh, actual tensor. Okay, and this is actually okay, so this is our actual tensor, and we need to see each time we get the slice chunks correct, right? And we need to find out that what exactly is wrong here. Uh, okay, so let's see if it slices correctly. Yeah, so this is actually the initial tensor. 4786 is the first chunk. 4786, that's right. And okay, how about if we get it tested using some LLM? Okay, this will be fine. Instead of us just checking each and every chunk, let's get it tested. Okay. Yes, this chunking is correct. First sample is correct. Okay, so let me show you a couple of results to verify that this tensor slice call function works well. Here is another one. Let's just copy this entire thing. So sometimes we have to be rigorous with testing and debugging because this is actually a very important part. So if you get the individual chunks of code or individual functions correctly, then your main logic won't be having much issues. This is exactly how you should debug low level tensor library. Short answer yes is 100% correct. Expected behavior, okay, this one is also correct, and let's just run it one more time. So here's another run. So let's just so here is another run. So we gave three examples, right? Three times, and yes, this actually gives a very strong clue about your MHA. Split is also almost correct, but not always, which explains something garbage. Okay. Full input tensor is this. Then you printed multiple blocks 16 cross 4. That's correct. Those tensors are supposed to be the heads after split for dimension 32 with 8 heads. Head dimension equals 4. Yeah, this is correct. Look at the first split block 4786. Compare with first four columns, the original one. So head 0 is correct. Now check second split. You printed this. Okay, head 1 is also correct. Now check third. Still correct. Okay. Columns are not contiguous in the memory. Okay. Alright, so looks like we found some issue with our tensor slice columns function. And let's see what exactly it is. Let's just see. So okay, so it says that those values appears earlier in the tensors in different columns. Okay, are you serious? Are you serious? Those values appear early in the tensor columns. You know what? This could it says that it says it found a particular head where the exact values were repeated, and since this is not actually the real time real live data, it's basically something we have generated, right? So it could be a matter of fact or a matter of coincidence that we might have generated exact same values. It could happen. It could happen. This is a classic stride bug. Okay, so the root cause is okay, let's just see. So it says that this is a classic stride bug. Okay, so now the last two blocks start going weird and duplicated patterns appear. Look at the last two heads. Okay, last two heads, fine. Okay, so here's the last one and here's the second last. So 3 1 3 4. Okay, and 3 1 3 4, and what else? 8 6 10 3. uh, 3 1 3 4 3 1 3 4 8 6 10 3, right? Okay. Yeah, so 3134 is fine. 3134 will have 317, something like this. So 3172 8610 3. So you see 8610 3. This is 8646. So 8610 3. Yeah, this is 8610 3 and 6658. The next should be 6658. So yeah, 6658, and then we have 7910 3, and then 8226. So um 7 9 10 3 8 2 2 6. Seems like this logic is fine. This tensor slice method is fine. I disagree with ChatGPT or LLM because that's the problem. Sometimes you feel like, okay, LLM or ChatGPT, whatever it is, gives you just perfect verification, and when you sort of start verifying, you'll see that you know it just hallucinated, and that's why you should not take any sort of help with LLMs. That's what happens all the time. So we have blocks starting with 10 8 8 7 7 9 1 3. Okay, 10 8 8 7. So you have blocks starting with 10 8 8 7. Okay, 10 8 8 7. Okay, something like yours is using contiguous memory logic, something like this. This is wrong for row measure matrices because the columns are not contiguous in the memory. Yeah, that's right. Memory layout of row major, so columns are shredded. R times columns plus C, and so copying columns row by row. Copy. Y bug appears randomly. Sometimes your contiguous memory that looks contiguous enough, so it works. Then allocation layout changes. Garbage. But what exactly is wrong with this particular output? I don't think if there's anything specifically wrong with this particular output. And okay, starting with um, okay, what to test next. Alright, so now mm, yeah, I guess this should be out columns rather than columns, right? No. Alright, so seems like it's working now. So actually the problem was, um, you know what? The problem was something was wrong in our concatenate method, and I just tested it over here, if I'm able to show you. So there's something called cycle check. So cycle check means that if you have some tensor, you just split that tensor and you just creates small chunks of tensors in the columns dimension, and you have all those chunks available. You're storing that in some array, and then you're looping through that array and then concatenating them again, and you're just ensuring that making sure that the starting tensor is equals to uh, the derived or the obtained tensor after splitting and the concatenation operation. If those two tensors are okay, it means that your slicing and concatenation logic just worked perfectly. And this is what I tested. I took a break because it was taking a very long for me to trace out what exactly is wrong. So it took excruciating effort. So to finally test it, so I written a method called tensor equal, and what it takes is actually is the concatenated output and the initial tensor. These should be same. So I went through, I created all the chunks, right? These are the chunks, and I just kept on appending into some array which is defined over here, and then I took all these pieces, head array and number of heads. So I looped through and I checked whether both these concatenated and initial tensor are okay or not. So it was just working fine. I was getting 1 all the time. 1 means that they're both equal, and 0 means something is wrong with the tensor. So once that worked, it was just a matter of um, uh, making sure that the obtained tensors are row major. And what do I mean by row major? Is basically the PyTorch or JAX or some TensorFlow, the heavy frameworks. What they do actually is they create a stride abstract as well. And by stride abstract, I mean that every operation, every obtained tensor depends upon the stride, not something r times columns plus c. What we are doing actually row major indexing. They don't do like this. They use one abstract stride, which eliminates 80% of their problems. And since this is just for the education purposes for now, we are we just ensure that every output should be row major. And by row major I mean that inside the memory in C, what happens basically is you have a 2D tensor which is stored in one contiguous buffer, which I've explained previously. A lot of the times you can see my previous videos. So what happens basically is every row is stored in a every row of a matrix is stored on contiguous block, and then comes the other row, and then comes the other row. So number of times, however many rows we have. This is called row major sequence. And in column major is exactly the opposite. We have columns placed inside arena, inside one giant block, a straight buffer, one after the other, right? So at some point we were actually getting the column major tensor instead of row major, and that's why our calculations were not working. And this is probably due to the concatenation, wrong logic in concatenation. I accidentally looped number of columns times, which is the outward columns. Have looped um, I should have looped uh, head dimension times instead of a big tensor. So this is actually the main problem over here. So we've managed to resolve this, and now if I show you, so this is actually our main file. So I'm putting an exit check over here. I just wanted to see that whether the multi-head attention for pass is working fine. And as you can see, I'm now getting the tensor. This is actually the tensor 16 cross 32 after attention score, and everything is working fine. So we have successfully built our graph um, till the multi-head attention. And yeah, so Now we need to keep on building this graph for feed-forward neural networks and layer norm 2, and if everything works fine, then we'll be ready for backward pass, and I will see you then.